Have you ever wondered how we can measure an unknown resistance without even measuring current or voltage directly? That's where the Wheatstone Bridge comes in, a classic circuit used to measure unknown resistance accurately using the principle of balance. The Wheatstone Bridge consists of four resistors arranged in the shape of a diamond. A battery is connected across one diagonal and a galvanometer across the other. We label the corners as points A, B, C, and D. The battery is connected across points A and C. This is called the battery arm. The galvanometer is connected across points B and D. This is called the galvanometer arm. This bridge is used in real devices like meter bridges and strain gauges. Now let's understand how the bridge works. When the bridge is not balanced, electric current flows through all four resistors and also through the galvanometer. We denote this current through the galvanometer as capital I sub G. Let me spell that out, capital I with subscript G for galvanometer. I sub G. If the bridge is not balanced, then I sub G is not equal to 0. To use the bridge for resistance measurement, we adjust one of the resistors until the galvanometer shows no deflection. That means I sub G is equal to 0. This is called the balanced condition. At this point, the potential difference between points B and D becomes 0 and no current flows through the galvanometer. This condition is essential for calculating an unknown resistance using the balance formula. Let's derive the condition for balance in the Wheatstone Bridge. Label the resistors in the bridge as R sub 1 in arm A to B, R sub 2 in arm B to C, R sub 3 in arm C to D, R sub 4 in arm D to A. Suppose the currents in the upper and lower branches are I sub 1 through A, B and C, D, I sub 2 through B, C and D, A. At balance, I sub G equals 0, so we can apply Kirchhoff's loop rule in two closed loops. First loop, from A to B to D and back to A. Second loop, from C to B to D and back to C. In loop A, B, D, A, we write negative I sub 1 multiplied by R sub 1 plus I sub 2 multiplied by R sub 2 equals 0. In loop C, B, D, C, we write negative I sub 1 multiplied by R sub 3 plus I sub 2 multiplied by R sub 4 equals 0. Now, divide both equations to eliminate the current terms. We get R sub 1 divided by R sub 2 is equal to R sub 3 divided by R sub 4. This is the balance condition for the Wheatstone Bridge. Now let's apply the balance condition to measure an unknown resistance. Suppose R sub 4 is the unknown resistance. If the bridge is balanced, that is, the galvanometer shows no deflection, we can rearrange the balance equation. We start from R sub 1 divided by R sub 2 equals R sub 3 divided by R sub 4. Cross multiplying gives R sub 4 equals R sub 2 multiplied by R sub 3 divided by R sub 1. So by knowing three resistances, R sub 1, R sub 2 and R sub 3, and adjusting R sub 3 until the bridge is balanced, we can calculate the unknown resistance R sub 4. This is a very precise way of measuring resistance without directly using an ohmmeter. Let's test the balance condition with actual values. We are given R sub 1 equals 100 ohms, R sub 2 equals 10 ohms, R sub 3 equals 5 ohms, R sub 4 equals 60 ohms. Let's check the balance condition. Let's start with the left-hand side. R sub 1 divided by R sub 2 equals 100 divided by 10. Right side, R sub 3 divided by R sub 4 equals 5 divided by 60. That gives 0.0833. Now compare. 10 is not equal to 0.0833. Therefore, the bridge is not balanced and there will be current through the galvanometer. This tells us that R sub 4 needs to be adjusted if we want the bridge to balance. Let's wrap it all up with a quick recap. A Wheatstone bridge is a circuit with four resistors, a battery, and a galvanometer arranged in a diamond shape. The bridge is balanced when the galvanometer current, I sub G, is 0. The balance condition is R1 divided by R2 is equal to R3 divided by R4. When balanced, the unknown resistance R sub 4 can be calculated using R sub 4 equals R sub 2 multiplied by R sub 3 divided by R sub 1. This bridge is used in meter bridges for lab experiments, strain gauges to measure mechanical stress, temperature sensors that rely on resistive changes. So next time you work in the physics lab, or even use a smart device with a sensor inside, remember, there's a Wheatstone Bridge quietly doing its job in the background. See you in the next session.